We will start with the left Riemann sum, and throughout this video I'm going to be using diagrams from the very excellent review on Khan Academy's AP Calculus site, and this is one of them. So we have a graph here, f of x, that's an increasing graph, and for the left Riemann sum, we're going to go from x equals 0 to x equals 4. So if you create a number line here with possible endpoints, okay, we're going to go from 0, 1, 2, 3 to 4. And what you notice is if you're doing a left Riemann sum, only these 4 points are going to appear on the graph. There will be no f of 4. You could see here's x equals 4. There is no point that's on the graph. So I'm going to create a little phantom hole here to emphasize that. So the way you draw these, folks, for a left Riemann sum, you go to the left upper corner. The points on the graph are going to be the left upper corner of each of the rectangles. So you could see here, this is the left upper corner of rectangle number 1, number 2, number 3, and number 4. You're going to go to the f of position on the graph. So here, we're going to go to the f of 0, and then we're going to draw a horizontal line until we reach the point where we're above or below the next f of point. And right there, we're below f of 1, we are going to stop. So if we're doing a left Riemann sum, our horizontal lines are going to run from left to right. Okay, now we're going to get to the next f of spot on the graph. We're going to draw a horizontal line until we get to the area above or below the next f of point. We're going to stop here. We're going to do the same thing. Then we're going to get up to here, and now we're going to stop where the phantom f of point is, right there. And that is how you draw your rectangles for a left Riemann sum. Now, in terms of the math, it's going to be the delta x times f of these left 4 points of the graph, the f of these left 4 points on the number line added together. So plus f of 1 plus f of 2 plus f of 3, but notably absent is there is no f of 4 included in that sum that you're going to multiply by delta x. Next, looking at this graph of the right Riemann sum, again from Khan Academy, we have our number line. But this time, for the right Riemann sum, we are not going to have an f of 0. We're only going to have an f of on these 4 points. So you could see we have an f of 4, 3, 2, and 1, but notably absent is f of 0. I'm going to go ahead and put a little phantom circle here indicating that we do not have f of 0 on this computation. Okay, so what do? This is a right Riemann sum, so we're going to draw our horizontal line from right to left. So we're going to get on the furthest rightmost point that's on our number line that we're going to include in terms of the f of, and here we go, we have f of 4. We're going to run a horizontal line going from right to left until we hit the area above or below the next point, and we stop our horizontal line. Then we're going to go to the next f of point. We're going to run a horizontal line going from right to left until we reach the point above or below the next point on the graph. Similarly, we're going to do this. And finally, when we get to f of 1, we're going to go horizontally from right to left. We're going to stop above the phantom point. And then we're going to draw our rectangles straight down. Okay, when we do our math, it's going to have the same delta x, which is 1. So our delta x is going to equal 1, and our f ofs are going to include f of 1 plus f of 2 plus f of 3 plus f of 4. And notably absent is we do not include f of 0 in the math computation of the area. Next, we are asked to evaluate this Riemann sum for this function y equals x squared plus 1. You can see it's a parabola that's been translated 1 unit upwards, and we're going to ask for 3 intervals, and we're going to use the midpoint technique to draw our rectangles. So the first thing we want to do is draw our number line that includes the endpoints from -1 to 2. So we have -1, we have 0, we have 1, and we have 2. Now, if we're going to be using the midpoints, the f ofs are going to be right at the midpoint of these 3 intervals. So we're going to have these 3 locations for our f ofs. This is going to be -0.5, this is going to be +0.5, and this is going to be 1.5. So we're going to go to our graph at each of those locations. So here's -0.5, here is +0.5, and here is 1.5. Okay, when you draw your midpoint rectangles, you get to the f of point, and now you draw your horizontal line in both directions until you get to the endpoint that is on either side of the midpoint. So here I went to the right until I got above the 2 right here, and then I went to the left until I got above the 1, because 1.5 is between 1 and 2. Okay, the next thing I'm going to do is go to the next midpoint here, and I'm going to draw a horizontal line to the right. This is at 0.5 here. I'm going to make a horizontal line to the right until I get to the 1, and then I'm going to go to the left until I get to the 0. Next, I'm going to go to this midpoint at -0.5, and let me do a different color. I'm going to go to the right until I reach the 0, because this -0.5 is between 0 and -1, and then I'm going to do a left horizontal line until I get to that -1. Again, that's because that -0.5 is between 0 and 1. Then I'm going to go ahead and draw my rectangles, and now we could talk about the math. So the math is going to be delta x times each of these f ofs. And what are the f ofs going to be? It's going to be f of -0.5 plus f of 0.5 plus f of 1.5. That will get you the estimation using the midpoint formula in this scenario. Here's another example where the midpoint formula is used, or the midpoint technique is used, and the rectangles have already been drawn in. So here we go. Here are our endpoints, and here are the midpoints, and here's f of the midpoints on each part of the graph here in pink. So what was done is horizontal line was drawn to the right and to the left until you reach the 2 sides between which the midpoint exists, or I should say the 2 endpoints between which that midpoint exists. Here we go. We're going to go horizontal to the right until we reach that endpoint, horizontal to the left until we reach this endpoint. Same thing here, and same thing here. And then we draw our rectangles. Let's now discuss the trapezoidal formula, and we have an f of x function here that runs from an a value of 1 to a b value of 9. And we've indicated that here. We're going to create our number line. So let's first find our delta x. And by the way, we're asked to divide this into 4, n equals 4. N equals 4 means 4 subintervals. N equals 4 also means 4 rectangles. So what we're going to use first is the formula of b minus a over n, which in this case is 4, and we get our delta x value is going to be 2. So let's go ahead and divide this distance here into fourths, and then we're going to march by a delta x of 2. So this becomes 3, this becomes 5, this becomes 7. Okay, now what's different about the trapezoidal formula is all of these are going to be featured on the graph. All of these are going to have an f of. So here we go. We have f of 1, f of 3, f of 5, f of 7, and f of 9. And then we're just going to connect them with a line, like so. And that's how you draw the trapezoidal rectangles. Now, in terms of the math, the formula is as follows. The area is going to equal delta x over 2 times f of 1 plus 2 times f of 3, 2 times f of 5, 2 times f of 7. Let me put a 2 here. Okay, the first one, f of 1, is just once multiplied, just as is. And the final one is also just listed once. So let me just make some room up top. So we're going to have 2 times f of 3 plus 2 times f of 5 plus 2 times f of 7, but only 1 time f of 9. So again, it is these the middle f ofs get multiplied twice, but the ones on the end do not. And that is your formula to get the area using the trapezoidal sum. Folks, let's just spend a few moments on where this unique formula for the area of the trapezoidal sum comes from. Recall, this is a trapezoid here in the upper right. It's a four-sided figure where 2 of the sides are parallel. And you recall that the area of a trapezoid is the average of its bases. So b1 plus b2 divided by 2 times its height. But when we use trapezoids here in a summation problem, we don't use this orientation. So let me see if I can rotate this to show you what I mean. Okay, I'm going to make it smaller, and then I'm going to rotate it, and I'm going to bring it into our figure. This is the orientation. Let me make it just a little bit smaller. This is the orientation that we use of the trapezoid. So now, where these used to be the 2 bases here and here, and this used to be the height, this changes to f of this x, okay, f of x sub 0, f of this x, f of x sub 1, the average of those times delta x. So here, if we look at this first trapezoid down here, here's the formula for trapezoid number 1. We're going to have the average of these 2 distances, that's f of x sub 0 plus f of x sub 1 divided by 2 times delta x. Now, as we move to trapezoid number 2, let's look at its formula. We see that it's going to be the average of f of x sub 1 and f of x sub 2 times delta x. So here it is. Now, so what do you notice? F of x sub 1 is used in the formula for the first trapezoid as well as the second trapezoid. And when we go to the third trapezoid, we're going to find that f of x sub 2 was used in the formula for both the second trapezoid and the third trapezoid. And when we get to trapezoid number 4, we're going to see that f of x sub 3 was used in both the formula for trapezoid number 4 and 3. But notice, these two are only used once. So f of x sub 0 and f of x sub 4 are only appearing once in the formula, whereas the others appear twice. And that is because of what we just discussed right here. Folks, before we leave this formula, I just want to point out that all of these trapezoids have delta x times the average of the bases, and you could see what ends up happening is this delta x and this 2 get factored out in front, and we are left with all of the sums of the heights of each trapezoid, with the ones in the middle being included twice. Our focus to over and underestimation. So you see here that when you're dealing with the left and right Riemann sum, the only issue is whether or not the function is increasing or decreasing. Concavity does not matter. So with right and left functions, you can ignore concavity. Okay, so let's look at this first scenario where we have an increasing function and a left Riemann sum. So look what we did here. All the points on the graph, all the f ofs are in the upper left corner, and when we get to the point, we draw our horizontal line from left to right, and we create our rectangles. We stop at the next point, either above or below the next f of point. And you can clearly see that this is an underestimation. So the way to remember this is if you have a left Riemann sum and you have an increasing function, you will have an underestimate. LIU, like Long Island University. Now, when we go to the right Riemann sum, we are going to be on the upper right corner of the rectangle on the graph. F of on the graph. Here, that f of is excluded because this is a right Riemann sum. I forgot to mention that this f of is excluded because it's a left Riemann sum. There's a phantom spot there, just like there's a phantom spot here. Now, with the right Riemann sum, we're going to draw our horizontal line from right to left. And you could see that we're stopping when we're above or below the next f of point. Here we're above the next f of point. And clearly, when you have a right Riemann sum, this is an overestimate. Because look, we have some element of the rectangle that is above or over the function itself. So, if you just remember, folks, LIU, everything else can be figured out. So let's take these words, or I should say this acronym. Can I move that? No. Let's take this acronym and right underneath it, we're going to write a right increasing function. So here, this stays the same. This is the opposite. So let's think of that as a negative sign. So we have one opposite. We have one negative sign. That means this is going to be opposite to the underestimate. So this is going to become an overestimate. Right increasing overestimate. Next, I want to illustrate, folks, that concavity does not matter when you're talking about a left and right Riemann sum and you're talking about over and underestimation. Here, I have an increasing graph that's concave down in contradistinction to the ones we just talked about, which were increasing and concave up. Again, increasing and concave down. So let's go ahead and do a left Riemann sum here, and we're going to predict that there's no change. We're still going to have LIU going on here. Okay, so let's do a left Riemann sum. We're only going to do one rectangle. That means our rectangle, we're going to start on the left, and we're going to draw a horizontal line from left to right until we are above or below the F of point. There's a phantom point. There are no points there on the graph. We're going to draw our rectangle down, and clearly that is an underestimation of the graph. Over here, we're moving to a right increasing graph. We're expecting an overestimation. We're going to put a point F of on the right side of the graph. This is going to be a phantom. We're going to go now with our horizontal line from right to left. We're going to stop when we're above or below the next F of point, and we're going to draw our rectangles, and you could see this is clearly an overestimation. So whether it's concave up or concave down does not matter. What matters is whether it's increasing or decreasing, as we'll see in a minute. Next, we're going to look at a decreasing function. And I'm going to show you how a decreasing function is what matters when you're dealing with left and right in terms of over or underestimation. Concavity is not going to matter. Okay, so we have a decreasing function. Let's first look at the left Riemann sum. I'm not going to talk about how we drew this because I've been over that several times already. Okay, in this left Riemann sum, let's just look at this acronym. Left increasing underestimate. Okay, so we're going to leave left the same. We're going to change to a decreasing function. So here, these are opposite. These are the same. We have one negative sign. If we have one negative sign, that means this is going to change to an overestimate. And indeed, you could see that this left Riemann sum is an overestimate. Okay, let's now look at the right Riemann sum and compare it to the Long Island University acronym. Okay, we're going to change this to right. We're going to change this to decreasing. Okay, so here we have the opposite. That's a negative sign. Here we have an opposite. That's the negative sign. Now we have two negative signs. That makes a positive. That means this is going to stay the same. And sure enough, you look at this decreasing right Riemann sum, and it is an underestimate. Just like a left increasing is an underestimate, a right decreasing is an underestimate. Very quickly, let's just show that concavity does not matter when you're talking about left and right Riemann sums. So here, a few moments ago, we looked at a decreasing function that was concave down. Now we're going to look at two decreasing functions that are concave up. We're going to start with the left Riemann sum. We're going to go to the F of, we're going to draw a rectangle till we stop right there above the phantom. We're going to draw our rectangle, and clearly we see that this is going to be an overestimate. There's portions of the rectangle that are above the graph. So it does match with what we had a few moments ago with this concave down and decreasing function. Moving over here to the right Riemann sum. Again, we have a decreasing function. This time it's concave up. We're going to start, since this is a right Riemann sum, we're going to start to the right F of, and we're going to draw a horizontal line till we're above or below the next F of point. That's a phantom point, but we stop. We draw our rectangle down, and clearly this rectangle is an underestimate because there's portions above the rectangle that are still beneath the graph. Therefore, we confirm that we have a right Riemann sum decreasing. It's going to be an underestimate. It does not matter what the concavity is. Talk about trapezoidal functions. Recall with a trapezoidal function, the f ofs are represented on all of the points, and then you simply connect them. With trapezoidal estimates, it is the concavity that matters only. Increasing or decreasing is irrelevant. So here we have a concave down graph. Concave down. This portion of the graph is increasing, and it's concave down. And what do you notice? This is an underestimate because there's portions of the graph that are above our trapezoidal figure. Now, when we move to this part of the graph, still concave down, but now decreasing, we see that it's the same. This is still an underestimate. So what did we learn? Concavity matters. If you have a concave down graph, the trapezoidal sum is going to be an underestimate. It doesn't matter whether the graph is increasing and concave down or decreasing and concave down. The result is going to be the same. Increasing and decreasing is irrelevant. A concave down graph is going to be an underestimate with the trapezoidal sum. Continuing on our discussion with the trapezoidal rule, we have the graph shown here. On this portion of the graph, we see concave down. That means our trapezoidal figure is going to be an underestimate of the graph. But now, after we cross that relative maximum, we now have a concave up portion of the graph. Focus on the pink, if you will. Now, look over here. This is concave up, concave up, concave up. But here we change from a decreasing and concave up to increasing and concave up. But folks, it doesn't change with respect to the estimate. Here, if you're concave up, our rectangle is going to be an overestimate because portions of our rectangle are above the pink graph. When we change from concave up decreasing to concave up increasing, it's the same thing. So again, it's concavity that matters with the trapezoidal. So if you're concave up, you will be having an overestimate regardless of whether or not you are decreasing or increasing. If you're concave down, you will have an underestimate regardless of whether you're increasing or decreasing. Let's now turn our attention to the midpoint summation and whether it's an over or underestimate. Folks, the bad news here is that with a midpoint, it's hard to tell. Look at this graph here. We're using the midpoint. We're on the graph. We're going to the right and to the left. But look, here, this portion of this rectangle is above the graph. That's an overestimate. This is below the graph, so it's not easy to tell, and it depends where you are on the graph. So that's the bad news. The good news is, when you're dealing with midpoint, it's the opposite of trapezoidal, and trapezoidal is one of the easiest to figure out. So it doesn't matter what scenario you're in. So here we go. Here we're concave down and increasing. If you wanted to find what the midpoint is with respect to over or underestimate, you would do a trapezoidal drawing, and you can see that that trapezoid would be an underestimate of that graph. Here, we're concave up and we're decreasing. We would do a trapezoidal summation. Here we go. We could see that this trapezoid is an overestimate of the graph. Therefore, the midpoint would be the opposite. It would be an underestimate. Here, we're concave up and increasing. We're going to do a trapezoidal summation. We're going to see that this is an overestimate. Therefore, again, the midpoint is going to be an underestimate. And finally, over here, we're concave down and increasing. If we were to do a trapezoidal summation, we could see that's an underestimate. Therefore, the midpoint, it would be an overestimate. Okay, folks, here is a summary of what we talked about in this video. If you want to take a screenshot of this in our next slide, that might be helpful. Here, when we're talking about left and right, what matters is whether the function is increasing or decreasing. Concavity is irrelevant. All the answers can be emanated from this one acronym, LIU. If it's left, Riemann sum, and it's increasing, it's an underestimate. So let's change just one thing. If we have a right with an increasing function, right increasing function, only one thing changes. That increase stays the same. Left goes to right. Think of that as one negative sign. this will be the opposite and turn to a overestimate. Moving with a decreasing function, same thing, we're still going to use LIU. So what's going to change now is increasing to decreasing. If you have left decreasing, one thing changes, therefore you could think of that as one negative sign. This becomes opposite, so left decreasing is going to be an overestimate. Moving down here, if you have a right decreasing function, that's opposite, think of that as a negative sign. This is opposite, think of that as negative sign. The two negatives make a positive, there's no change. A right decreasing function is an underestimate. Continuing with the trapezoidal, remember, trapezoidal is easy to draw. All of the endpoints are represented on the f of graph. All that matters is the concavity. It does not matter whether the curve is increasing or decreasing. If you connect these points and you draw your rectangle, clearly this is going to be an underestimate if you are concave down. Alternatively, if you're concave up, you're going to get an overestimate. Also, don't forget that the trapezoidal sum area is the average of the left and right function. And the last thing to remember is that the midpoint sum estimate is going to be the opposite of what you see for trapezoidal. So if the trapezoidal estimate is an overestimate, then the midpoint is going to be an underestimate, and vice versa. It is difficult sometimes to intuitively figure out whether the midpoint is an over or under. So go ahead and get your trapezoid, decide if it's over or under, and for the midpoint you can report the opposite.